Right now, every cell in your body is holding an electric charge, not a metaphor, not a loose analogy, a literal voltage difference across every single cell membrane you own. 37 trillion cells, each sustaining an electric field of roughly 10 million volts per meter. Air breaks down into sparks at 3 million volts per meter. Your cell membranes hold 3 times that, continuously, without arcing, without failing, every second you are alive. A third of everything you eat goes to keeping those charges from collapsing. And the physics that describes how signals move through your nerves, the actual partial differential equation, was solved in 1855, not for biology, for a telegraph cable lying on the floor of the Atlantic Ocean. You are, in the most precise and literal sense, a battery. 37 trillion of them, wired together into the most complex electrical system in the known universe. And the cost of running it is staggering. Now, let me show you what I mean. Take any cell in your body. Pick one. A neuron in your brain, a muscle fiber in your hand, a red blood cell drifting through your heart. It doesn't matter which. Every one of them maintains a voltage difference across its outer membrane, about negative 70 millivolts inside compared to outside, 70 millivolts. That sounds like almost nothing. It sounds like a rounding error. The battery in your television remote is over 20 times stronger than that. But here is what changes everything. That 70 millivolts is not spread across centimeters or millimeters. It exists across the lipid bilayer, the thin fatty membrane that wraps every cell. And that membrane is about 7 nanometers thick, 7 billionths of a meter. So when you take 70 millivolts and divide it by 7 nanometers, you get the actual electric field strength inside that membrane, 10 million volts per meter. The electric field inside the insulation around your cells is stronger than the field inside a bolt of lightning. And it is there right now, in every cell, running continuously. You are sitting inside your own electric storm, and you cannot feel it. The physics here is not exotic. It is the same physics as a parallel plate capacitor, the kind you build in a first-year electronics course. 2 conducting layers separated by a thin insulating layer. Inside the cell, salty conducting fluid. Outside the cell, salty conducting fluid. Between them, a lipid bilayer that acts as the dielectric, the insulator. Same geometry as a capacitor in a radio circuit. Same equations. Your body builds 37 trillion of them and charges every single one. But where does the voltage come from? You see, the answer goes back to 1889 and a German chemist named Walther Nernst. He would eventually win the Nobel Prize in 1920, but decades before that he figured out something essential. If you have 2 solutions separated by a membrane, and one solution has a much higher concentration of a particular ion than the other, and the membrane is even slightly permeable to that ion, you get a voltage. The ions want to move down their concentration gradient, the way water runs downhill, but because ions carry electric charge, their movement creates an electrical potential that pushes back against further flow. The system reaches an equilibrium, a specific voltage that exactly balances the concentration difference. Nernst wrote down the equation. E equals RT over ZF times the natural log of the outside concentration divided by the inside concentration. And this equation, this exact equation, is used today in battery design, in fuel cell engineering, in corrosion science. Your cell obeys the same mathematics as a lithium-ion battery. Inside your cells, potassium concentration is high, about 140 millimolar. Outside, it is low, about 5. Sodium is the reverse. High outside at 145 millimolar, low inside at around 12. These concentration differences are enormous. And when you plug potassium's numbers into Nernst's equation at body temperature, you get negative 90 millivolts. For sodium, you get positive 60 millivolts. The actual resting potential sits between those 2 values, weighted by how permeable the membrane is to each ion. That weighting is described by the Goldman-Hodgkin-Katz equation, a refinement that accounts for multiple ions at once. The voltage across your cells is not generated by some mysterious biological force. It comes from ion gradients, compressed springs of chemical potential energy stored in concentration differences across a 7-nanometer membrane. Same physics as any electrochemical cell. Every cell in your body is a tiny battery, and Nernst's 1889 equation tells you exactly what voltage it will produce. And all of that electricity, 37 trillion cells firing, is measurable from outside your body. Every EEG reading of your brain, every ECG tracing of your heart, every EMG recording of your muscles. You radiate your own electricity. Other instruments can see it. Other organisms can sense it. But I will come back to that. First, there is something more urgent to understand. A third of everything you eat maintains this charge. And I have not told you why yet. Here's the problem. Those ion gradients, the high potassium inside, the high sodium outside, they are not stable. They are thermodynamically unstable. Sodium ions leak into your cells through tiny channels. Potassium ions leak out. Every second, the gradients are decaying. The voltage is drifting towards zero. Thermodynamics demands it. Equilibrium means equal concentrations on both sides, which means zero voltage, which means no electrical signaling, no muscle contraction, no heartbeat, no thought. Equilibrium for a living cell is the end. This is not a slow drift. This is an ongoing war. Your body is not maintaining electricity the way a battery sits on a shelf. It is fighting to keep electricity the way you fight to keep a boat from sinking, constantly bailing water because the leaks never stop. So every cell fights it, continuously, without stopping, for your entire life. The weapon is a protein embedded in every cell membrane called the sodium-potassium ATPase. It was discovered in 1957 by a Danish scientist named Jens Christian Skue, and the story of how he found it is worth knowing. Skue was studying crab nerves, not human neurons, not mammalian tissue, crab nerves. He was trying to understand how local anesthetics worked, and he kept finding this enzyme in nerve membranes that consumed ATP, the cell's energy currency, but only when both sodium and potassium were present. It made no sense to the biochemists around him. They were focused on the grand mechanisms of cellular metabolism, the electron transport chain, the citric acid cycle. An enzyme in a crab leg that needed 2 specific ions to function? It looked like a curiosity. For years, his work was largely ignored. Colleagues dismissed it. Journals showed little interest. A crab nerve enzyme? Who cared? But Skue understood what he had found. He saw what others could not, that this enzyme was not a curiosity. It was the pump, the molecular machine that pushes sodium out and potassium in, against their concentration gradients, burning ATP to do it. Each cycle, 1 molecule of ATP hydrolyzed, 3 sodium ions expelled, 2 potassium ions imported, about 100 cycles per second, billions of these pumps per cell, running non-stop from the moment you are born. It took 40 years for the scientific community to fully recognize what Skue had discovered. He received the Nobel Prize in 1997. He was 79 years old. 4 decades of persistence, starting with crab nerves in a small Danish laboratory. The cost of this pump is almost incomprehensible. Your neurons spend up to 70% of their total ATP production just running sodium-potassium pumps. 70% of a neuron's energy budget, not for thinking, not for signaling, not for forming memories, just for maintaining the charge. Brain-wide, the pumps consume 20 to 40% of all energy, and your entire body produces roughly 40 kilograms of ATP every single day. That is more than your own body weight, recycled over and over from ADP back to ATP, burned and rebuilt thousands of times. Of that 40 kilograms, somewhere between 10 and 15 kilograms is consumed exclusively by sodium-potassium pumps every day, just to keep 37 trillion capacitors from discharging. Think about what that means. Every meal you have ever eaten, a third of its energy went to an electrochemical war against thermodynamic equilibrium that you cannot feel, cannot see, and cannot survive without for even a few minutes. You are not a body that happens to use electricity. You are an electrical system that eats food to stay charged. And here is a detail that I find particularly beautiful. The pump is electrogenic. 3 sodium ions out, 2 potassium ions in. That is a net export of 1 positive charge per cycle. The pump itself generates a small current. It contributes about -3 to -5 millivolts to the resting potential. It is not just maintaining the gradient. It is a current source. A tiny generator embedded in every cell membrane, burning ATP, producing electricity, 37 trillion generators, each one a molecular engine smaller than a virus, running on the food you had for breakfast. So the picture now is very different from where we started. You did not just learn that your cells hold a charge, you learned that they hold a charge that is actively collapsing every second, and that a third of your metabolic energy goes to fighting that collapse. The voltage is not a feature, it is a war. And if the pumps stop, if ATP production fails for even a few minutes, the gradients dissipate, the voltage collapses, and the signals stop. But here's something I have not told you yet, and it changes the picture entirely. Having the charge is not enough. All of that energy, all of those pumps, all of that ATP, it maintains the voltage across 37 trillion cells. And that voltage is locally useless, because you almost cannot send it anywhere. A neuron is a long, thin cable. Some of them run from your spinal cord to your toes, about a meter. The signal traveling down that cable is a voltage disturbance, a brief depolarization rippling along the membrane, and it decays, fast. In an unmyelinated axon, the signal drops to 37% of its original strength within about 1/10 of a millimeter to 1 millimeter. That distance is called the length constant. A meter-long neuron with a millimeter-scale length constant means the signal is essentially gone before it has traveled 1% of the distance it needs to cover. You spend 1/3 of your food maintaining a charge that vanishes within millimeters of where it starts. Without amplification, a signal from your spinal cord would never reach your toe. It would disappear into nothing, like a shout into a hurricane. This exact problem was solved 60 years before anyone understood neurons well enough to describe them mathematically. In 1855, William Thomson, later Lord Kelvin, was consulting on the most ambitious engineering project of his era, a telegraph cable spanning the Atlantic Ocean from Ireland to Newfoundland. 3,000 kilometers of copper wire insulated with gutta percha lying on the ocean floor. And the signals kept degrading. Thomson analyzed the cable. Copper wire has axial resistance. It resists current along its length. The gutta percha insulation has capacitance. It stores charge between the wire and the surrounding seawater. And the insulation is not perfect. It leaks. Current escapes into the ocean. He sat down and derived the mathematics of voltage propagation in a lossy transmission line. A partial differential equation, tau times the partial derivative of voltage with respect to time, equals lambda squared times the second partial derivative of voltage with respect to distance minus v. The telegrapher's equation, mathematically identical to Fourier's heat equation, the same one-dimensional diffusion problem. A neuron has the exact same architecture. The axoplasm inside the axon is the copper wire, a resistive conductor. The lipid bilayer is the gutta percha insulation, a capacitive layer. The ion channels are the leaks, current escaping through the membrane into the extracellular fluid, which plays the role of seawater. Same geometry, same physics, same equation. Kelvin was describing your nervous system a century before neuroscience had the tools to know it. Thomson's solution for the telegraph was to place repeaters along the cable. Boost the signal at intervals before it decays below usable levels. His mirror galvanometer amplified the faint signals arriving after 3,000 kilometers. Queen Victoria sent a message to President Buchanan. It took 16 hours to transmit, but it worked. Victoria knighted Thomson in 1866. He became Lord Kelvin. Evolution arrived at exactly the same engineering solution, independently, hundreds of millions of years earlier. Myelin, a fatty sheath wrapped around axon segments by specialized glial cells. The myelin increases membrane resistance dramatically and reduces capacitance, which means less current leaks out and less charge is wasted storing on the membrane surface. Between the myelinated segments, there are small gaps, nodes of Ranvier, where voltage-gated sodium channels cluster densely. At each node, the signal is regenerated to full amplitude, not passively conducted, actively boosted. The signal hops from node to node. Saltatory conduction, from the Latin saltare, to jump. Same cable, better insulation. Strategically placed amplifiers. The result is extraordinary. Unmyelinated axons conduct at about 1 meter per second. Myelinated axons conduct at up to 120 meters per second. Touch your toe, and the signal reaches your brain in about 8 milliseconds instead of a full second. The difference between catching a ball and watching it hit your face. Kelvin and evolution, working on the same problem centuries apart, converged on the same design. Insulate the cable. Boost at intervals. This is not analogy. This is the same equation, the same physics, the same solution. But there is one organ in your body where the stakes are different from anything else. Your brain can afford brief lapses. A neuron misfires, another one compensates. Your muscles can rest. But your heart cannot wait. It cannot pause. It cannot afford a single missed beat, a single lost signal. And it solved this problem in a way that is, I think, one of the most elegant engineering solutions in all of biology. 10,000 cells in the upper right chamber of your heart, the sinoatrial node. Depolarize spontaneously. No signal from the brain. No external trigger. Your heart does not obey your brain. It is its own electrical authority. These cells have a peculiar ion current called the funny current. It was genuinely named that by the researchers who discovered it because it behaved opposite to every other known current. After each action potential, the funny current slowly depolarizes the cell until it reaches threshold and it fires again, self-resetting. A biological oscillator. 60 to 100 times per minute without any instruction from your nervous system. From the SA node, the electrical wave spreads across the atria, reaches the atrioventricular node, which imposes a critical delay of about 120 to 200 milliseconds, giving the atria time to finish contracting, then rushes through the bundle of His and its branches into the Purkinje fibers, which distribute the signal across both ventricles simultaneously. The entire ventricle depolarizes in about 80 milliseconds. Your heart is as much an electrical organ as a mechanical pump. In 1903, a Dutch physiologist named Willem Einthoven built a string galvanometer sensitive enough to detect the heart's electrical field through the skin. He named the waves he recorded P, QRS, T, labels still used today on every electrocardiogram in every hospital in the world. Einthoven received the Nobel Prize in 1924. What he was measuring was nothing but voltage differences generated by cardiac ion currents. The heart produces a rotating electrical dipole in three-dimensional space, and Einthoven's electrodes capture its projections onto different axes. Every ECG tracing you have ever seen is a time series of a rotating electric dipole. Pure electrodynamics readable through skin and muscle and bone. Put your hand on your chest. What you feel is not just a mechanical thump. It is the physical consequence of an electrical wave sweeping through cardiac tissue at that very moment, depolarizing millions of cells in a precise sequence that has not stopped since before you were born. And here is a design detail that separates you from being alive and not. A cardiac action potential lasts 200 to 300 milliseconds. A neural action potential lasts 1 to 2 milliseconds. The heart's is 100 times longer, because of a sustained calcium influx that creates a long plateau phase. During that plateau, the cell cannot be re-excited. It is absolutely refractory. This prevents the heart from tetanizing, from contracting and staying contracted the way a skeletal muscle does when stimulated too rapidly. If your heart could tetanize, a single burst of abnormal electrical activity would lock it in permanent contraction, and that would be the end. The long refractory period is not a limitation. It is the single most critical safety mechanism in your body. When that coordinated pattern breaks, When regions of the heart start firing independently, chaotically, out of rhythm, that is fibrillation. The heart quivers instead of pumping, and a defibrillator does not restart the heart. That is one of the most common misunderstandings in medicine. A defibrillator delivers a massive electrical pulse, 200 to 360 joules in about 5 milliseconds, that depolarizes every cardiac cell simultaneously, resets them all to the same electrical state. Then the SA node, that self-oscillating pacemaker, reestablishes coordinated rhythm from scratch, not restarting, synchronizing, using electricity to restore electrical order. Now I want you to consider something. Everything I've described, the voltage across your membranes, the pumps that maintain it, the cable physics that transmits it, the self-oscillating rhythm of your heart, these are not hidden processes that require special instruments to detect. You radiate. And this is where the picture shifts one final time. You are not a body that happens to produce some electricity as a byproduct. You are an electromagnetic system, and other living things can see you. In 1924, the same year, Einthoven received his Nobel Prize. A German psychiatrist named Hans Berger placed electrodes on a patient's scalp and recorded oscillating voltages. 10 to 100 microvolts. Faint, but unmistakable. The electroencephalogram, the EEG, was reading the synchronized postsynaptic potentials of billions of cortical neurons. Your thoughts produce measurable voltage patterns on the surface of your skull. The magnetic fields are even more remarkable. Every electrical current generates a magnetic field. That is Maxwell's physics, fundamental electrodynamics. The currents in your neurons produce magnetic fields of about 100 femtotsla. That is 100 millionths of a billionth of a Tesla, a billion times weaker than Earth's magnetic field. And yet, using superconducting quantum interference devices, squid sensors, we can detect them. Magnetoencephalography. Your thoughts have a magnetic signature. Faint beyond anything you would imagine possible to measure, but real and measurable from outside your head. Sharks have structures called the ampullae of Lorenzini, gel-filled canals in their snouts that can detect electric fields as weak as 5 nanovolts per centimeter. Every time a fish contracts a muscle, ion currents flow across its cell membranes and generate a faint bioelectric field in the surrounding water. The shark senses it, hunts by it, can find prey buried in sand, invisible, motionless, but electrically alive. The electricity that your cells produce is not just detectable by laboratory instruments. It is detectable by other living things, in real time, in nature. And some organisms took the same 70 millivolt membrane physics that keeps you alive and turned it into a weapon. Torpedo rays stack roughly 5,000 specialized cells called electrocytes in series. Each electrocyte generates about 100 millivolts when it fires, the same membrane potential as any of your cells. 5,000 cells, each contributing 1/10 of a volt, wired in series. 500 volts. Enough to stun prey, enough to injure a human. Same physics, same membrane, same ion channels. The only difference is architecture. How many cells, wired in what configuration? The building block is identical to yours. Every thought you have ever had, every heartbeat, every muscle contraction, all of it is electrical. Voltage changes across lipid membranes, governed by Nernst's equation, maintained by Scal's pumps, propagated by Kelvin's cable physics, and it does not stay inside you. You run on electricity. Every cell holds a charge that Nernst's 1889 equation describes with the same mathematics used for industrial batteries. Every neuron transmits signals using cable physics that Lord Kelvin derived for Queen Victoria's telegraph wire in 1855. Scal's pump. Discovered in crab nerves, dismissed for years, vindicated with a Nobel Prize 4 decades later, burns 1/3 of your daily food just to keep those charges from collapsing into thermodynamic equilibrium. Your heart generates its own rhythm through self-oscillating ion channels that fire without permission from your brain. And Einthoven proved in 1903 that its electric field is strong enough to read through skin and bone. 37 trillion batteries, each holding 10 million volts per meter across a membrane thinner than a wavelength of light, maintained by molecular pumps that consume more ATP each day than you weigh, connected by cables that obey a Victorian telegraph equation, coordinated by a self-firing oscillator that cannot afford to stop. And right now, somewhere in the ocean, a shark could find you by the electricity your cells cannot stop making. The same membrane, the same charge, the same physics that Nernst wrote down in 1889, that Kelvin solved for a copper wire on the ocean floor, that Sco spent a career defending, that Einthoven read through skin. 4 scientists across a century, each solving one piece of the same machine. The machine is you, and you have been broadcasting since before you were born.